Hi everyone, in this video we are going to very quickly practice distinguishing between alpha and beta decay. But before we jump into our two big problems, I have to ask you a very simple, easy one, hopefully easy. But you need to go through and tell me what each one of these symbols are. So there are 5 different things and I just want the name. What is that? Is that a fruitcake? Is that a chicken? Is it an alpha particle? What is it? Go. Alright, hopefully you got an answer. If not, this is something you need to stop and make 5 quick flashcards for, because these are things you just have to have memorized and there's no other way around it. You just have to memorize them. So the very first one is what we call an alpha particle. An alpha particle is really fat, it's really big, it takes up a lot of space, and it's represented by helium-4. Okay, helium always has an atomic number of 2, and so we always write our alpha particle as helium-4 with an atomic number of 2. Alright, B. This is what's called a gamma particle. A gamma particle has 0 for its mass number and it has 0 for its atomic number. So anytime you see 0 and 0, you should immediately be thinking gamma, gamma, gamma. Very tiny, but very high energy. You never ever want to interact with gamma rays if you can. Alright, C. C is indicative of an electron, but electron is not the word we actually use when we're talking about radioactive decay. So when we're talking about this electron, we actually call it a beta particle. So now a beta particle is something that is larger than a gamma particle, but smaller than an alpha particle. So that is one of the most important things that we can distinguish here. For an electron, we always say that it has a mass number of 0 and an atomic number of -1. Now, P, hopefully right away made you think proton. And a proton always has an atomic number of 1, which means its mass number has to be 1. Sometimes you'll hear people refer to it as hydrogen, as a proton. Keep that in the back of your mind for when we hit the very last module of this semester. It will come back and you'll kind of hopefully understand a little bit more about that. And then the very last one we have here is what's called a neutron. Neutron is represented with 0 for atomic number, 1 for its mass number, and we use a little n, not a capital N. If you do a capital N, people will think you're talking about nitrogen. So make sure you use a small n. Same thing for the proton. It has to be a lowercase p. If you use a capital P, people will think you're talking about phosphorus. Alright, so now let's dive into real stuff here. We've already shot a video on balancing nuclear equations, so I'm not going to take a lot of time to do this. I'm just going to ask you to solve these 4, and then tell me, after you've solved them, is it alpha or beta decay? Go. Alright, did you get an answer? Like I said before, I'm not going to spend a lot of time showing you how to solve these. Hopefully that's something you already understand how to do at this point. But the basic thing you need to do is make sure that your superscripts on your product side equal your superscripts, or the sum of your superscripts on each side for reactant and product side. Same thing for super and subscripts. So your mass numbers have to be equal to each other and your atomic numbers have to be equal to each other. So let's start off with this first one. We have 241 for the superscript, so we know that 237 plus something has to give us 241. The only way you could solve this properly is with having a 4 for the mass number. Now we're going to look at the subscripts. We have 95 here for our reactant side, and we have 93 on our product side. So 93 plus something has to give us 95. The only answer we have there is 2. Anytime you see 4 and 2, you should immediately be thinking that you have an alpha particle, so you'd write it as He. If you're not there yet, you can see that 2 is the atomic number for helium by looking at the periodic table. Then you could end up with your 4,2 helium or helium-4. Definitely an alpha particle. This is definitely alpha decay. Let's move on to our next one for B. Alright, so for B, what we're looking at here is we're going to start by balancing our mass numbers, or our superscripts. What I see is that we have 175 on the reactant side and 171 on the product side. The only way you can balance this out is by saying 171 plus 4 is equal to 175. So our mass number is balanced. Now we have to balance our atomic number. 78 on the reactant side, 76 on the product side. So 76 plus 2 is going to give me 78. Again, right away when you see 4, 2, you should be thinking alpha, 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 alpha. This is definitely an alpha particle, meaning that we have alpha decay for the overall nuclear equation. Alright, let's move to C. So now for C, it's a little bit different. So we see we have 247 on the reactant side, 247 on the product side. The only thing we could possibly put here is 0 for our mass number. So again, if we're looking at alpha or beta, right away you should be like, oh, I know what this is. Alright, but let's just check and make sure. So we have 95 on our reactant side, 96 on our product side. If it ever goes up from reactant to product, you know you have to have a negative number. And the only negative number we talk about here is -1. So immediately you're thinking, oh my goodness, this is an electron. This must be beta decay. All right, we have one more here. Let's look at this last one. So we have a 99 for each side on the top. The only thing our mass number could be is 0. And let's look at the bottom. Again, you should be thinking, oh, this is beta, this is beta, this is beta, but let's just check. So we have 43 on our reactant side, 44 on our product side. Again, it went up. If it goes up, you have to have a negative number here. So we have a negative number for its mass number, its atomic number, very indicative of an electron, definitely beta decay. Hopefully this makes sense. You have one more chance to master this, at least through this video, so give it one more shot if you weren't good there yet. 4 more, same exact question. We've just kind of switched it up a little bit. Instead of saying it's definitely alpha or beta, now you have to actually solve for this other component. Go. All right, did you get an answer? Hopefully you did, but this was definitely more challenging than question 2, so if you ran into a little trouble, please don't get frustrated. So let's start off with A. The first thing we have to do is figure out our missing component, and then we can decide if this was alpha or beta decay. So the first thing I'm going to do is balance my superscripts or my mass number. So what I see is I have 82 on my reactant side, 0 on my product side, so the only number this could possibly be is 82. 82 plus 0 definitely gives me 82. That works. All right, so now let's balance our atomic number. I see 35 on my reactant side, negative 1 on my product side. So this number actually has to increase. Instead of 35, we have 36. So 36 minus 1 definitely gives me 35. My numbers check out. Now what we have to do is go to the periodic table and figure out which element has 36 protons. I did this earlier, and I definitely found out that the one that has 36 protons is called krypton, and it has the symbol of Kr. Now, is this alpha or beta decay? Hopefully you were able to answer that without even doing this part that we just did of solving this whole component, because right here, that is a beta particle. So right away, you should be able to say that is definitely beta decay. Let's move to B. All right, so for this one, we're looking at neptunium, and we're trying to figure out what we create with this alpha particle, okay? So right away, you can look at this and say, oops, alpha, done. All right, so now let's solve for the missing component, though, just for practice. We have 237 on the reactant side, 4 on the product side, so we need to figure out what plus 4 gives me 237. The only way this math would work out is if we end up with 233 for our mass number. So let's check. 233 plus 4 definitely gives me 237, so we're good. Now we have to figure out the atomic number. We have 93 on the reactant side, 2 on the product side. So we need to figure out what number plus 2 gives us 93. Simple math. 91 plus 2 gives me 93. The only symbol or only element that has 91 protons is something called protactinium, which has a symbol of Pa. All right, we already decided it's alpha decay, so we can move on to C. So let's figure out what we're missing here. We have 149 on the reactant side, 4 on the product side, so something plus 4 gives me 149. Only way we can do this mathematically to make it work is to end up with 145. So let's check. 145 plus 4 definitely gives me 149. We're good. So let's do the other one. We have to do the atomic number. And so for the atomic number, we have 64 on the reactant side, 2 on the product side, so something plus 2 gives me 64. The only number we could have here would be 62. And so if we look at our periodic table and figure out which element has 62 protons, it is what's called samarium, Sm. Now we're trying to figure out alpha or beta decay. We can look right here, definitely alpha decay. You don't even have to do the math to figure that part out. That's the one thing I'm trying to drill through your head. I really hope that's making sense. All right, so now let's look at this last one here. We have strontium 90, and we're releasing an electron, essentially going through beta decay. So what we have to do now is figure out what our mass number is. So 90 has to be equal to something plus 0, which is definitely 90, right? That's the easy one. So let's figure out what our atomic number is. 38 has to be equal to something plus a negative 1. So our number, remember, our atomic number has to go up. So instead of 37 going down, it has to be 39. We went up. So 39 minus 1 gives us 38. Definitely correct. Now we need to check ourselves and figure out what our actual element is. Go to the periodic table, figure out which element has 39 protons. The only one that has that is yttrium, which is represented by the capital Y. We've already decided that it's beta decay, so we're done with this problem. Hopefully that helps, and now you have a better grasp on both balancing nuclear equations but identifying alpha and beta decay. The biggest thing you can do is just find that alpha particle or find that beta particle, and then the hardest part's over and you just assign alpha or beta. Very simple. I hope you understand. Have a great week. Take care of yourself and drink water.